the oldest light in the universe. Imagine a time before stars, before galaxies, before atoms as we know them. A time when the universe was nothing but a seething, glowing soup of energy and particles. Then, in an instant, the fog lifted. Light was born, and that light never stopped traveling. Today, more than 13.8 billion years later, that same ancient light still echoes across the vastness of space. Faint, cold, but everywhere, that same ancient light still echoes across the vastness of space. Faint, cold, but everywhere. It is called the cosmic microwave background, or CMB, and it is the oldest light we can observe. But where did it come from? Why is it still here? And what secrets does it hold about the origin of everything? This is not just a story of photons and temperature maps. This is the ultimate detective story about time, space, and the beginning of reality itself. A single photon from the dawn of time still travels through space, tracing the ancient light across cosmic history. The cosmic microwave background, CMB, is the fossil radiation from the Big Bang, a spherical shell of ancient light that surrounds us in every direction. A faint afterglow that fills the entire universe. It was first discovered by accident in 1964 by Arno Penzias and Robert Wilson, two radio astronomers working with a horn antenna in New Jersey. They were trying to eliminate a persistent background noise, and what they found was the first direct evidence of the Big Bang. This ancient light is incredibly uniform, coming from all directions in space with nearly the same intensity, but not perfectly, and those tiny fluctuations or anisotropies are what make it scientifically priceless. The CMB is everywhere. It surrounds us like an invisible shell. Its temperature is about 2.7 to 5 Kelvin, just above absolute zero. It has a black body spectrum, meaning it is nearly perfect thermal radiation. It originated approximately 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form and photons to travel freely, a moment known as recombination. To understand the origin of the CMB, we need to go back, far back, to a time when light couldn't move freely. For the first 380,000 years after the Big Bang, the universe was like a foggy plasma, a dense, hot soup of protons, electrons, and photons. Any photon that tried to travel was instantly scattered by free electrons, like headlights in a thick cloud. This era is called the photon baryon fluid stage, a period of constant collisions and radiation pressure. The universe was completely opaque. But as the universe expanded, it cooled. Eventually, it reached a critical temperature of about 3000 K. At this point, electrons combined with protons to form neutral hydrogen atoms. Suddenly, photons no longer had anything to scatter off. The universe became transparent. This moment, known as recombination, or last scattering, is when the CMB was born. The light that had been trapped for nearly 400,000 years was finally free, and it's been traveling ever since. How we observe the CMB. Modern cosmology owes much of its progress to our ability to observe and measure the CMB with astonishing precision. Key missions. COBE 1989 confirmed the blackbody spectrum of the CMB with extraordinary accuracy, earning a Nobel Prize. WMAP 2001 to 2010 mapped tiny temperature variations across the sky helping refine models of the early universe. Planck 2009 to 2013 provided the highest resolution map of the CMB to date, allowing cosmologists to measure the age, composition, and geometry of the universe. Each mission revealed more structure in the CMB, not random noise, but subtle patterns of hot and cold spots, the quantum fingerprints of the infant cosmos. These temperature differences, as small as 1 part in 100,000, correspond to density fluctuations in the early universe. Regions where matter was slightly denser began collapsing under gravity, eventually forming galaxies, clusters, and cosmic filaments. In a way, the CMB is a baby picture of the universe taken just after it was born. The physics of fluctuations, how quantum jitters became galaxies. At first glance, the CMB looks astonishingly smooth. But zoom in and you see minute fluctuations in temperature and density. These fluctuations are not random. They are quantum imprints stretched across the universe by cosmic inflation. According to inflationary theory, the universe underwent an exponential expansion, a tiny fraction of a second, after the Big Bang, growing from subatomic scales to macroscopic size in less than 1032 seconds. This dramatic expansion magnified tiny quantum jitters in the early energy field, freezing them into density variations. These fluctuations seeded all the structure we observe in the cosmos today. Slightly denser regions had more gravity, attracting more matter over time. Less dense regions became voids, vast expanses of emptiness. The CMB acts as a snapshot of this process, revealing the universe's structure just moments after inflation ended and matter began to coalesce. By analyzing the statistical distribution of hot and cold spots in the CMB, scientists can test theories about the early universe, the nature of quantum fields, and the physics of inflation itself. The pattern of fluctuations follows a specific power spectrum, a graph showing how temperature differences vary across angular scales. This power spectrum has peaks and troughs that match predictions from the CDM model, lambda cold dark matter, the leading cosmological model today. One of the most important results from Planck and WMAP is the match between theoretical predictions of inflation and the actual distribution of CMB fluctuations. This match strengthens the case that inflation really happened and that quantum mechanics shaped the entire cosmos. Thank you for exploring the origins of the universe with us. If you enjoyed this journey through time and space, don't forget to like, subscribe, and share this video with others who love science and the cosmos. Hit the bell icon so you never miss our next cosmic adventure.